Video, we covered the idea of how to tell whether a function was concave up or concave down kind of by looking at it or by looking at its derivative or its second derivative. So as a real quick recap of that, suppose that I gave you some function like this. That looks pretty good. I could ask you, okay, where are the points of inflection? I think that's a good question. Can you identify where the points of inflection of this graph are? So the points of inflection should mean, and keep in mind this is the original function f of x, points of inflection should be about where does concavity change. So as you're looking at this graph, how does this graph start out? Like what type of concavity does this have? And hopefully you recognize, oh yeah, that's concave down. This function is concave down, concave down, concave down, until somewhere right around in there. And at that point, the graph stops looking sad and starts looking happy, and so you've got this little sort of happy section here. And then at some point, we sort of hit the, like the steepest slope there. And after that point, it starts to be looking sad again. So what you've got is a region here that's concave down, a region here that's concave down, a region here in the middle that's concave up. And then these points in between here are those points of inflection, the points where it changes from being concave down to concave up, or from concave up back to being concave down. The previous lesson was all about looking at a graph and seeing those things. In the lesson that we have today, it's about how do we take a function, how do we do derivatives, how do we do calculus, and actually find those intervals. And so in the next slide, I'm going to go through the 5-step process for how we do that, and then I have 1 or 2 examples. So we'll get to that next. I'm virtually certain that the bell is going to ring either in this slide or in the next one, so I'll warn you now. The steps in the test for concavity. So first of all, it's called the test for concavity. It's not called the second derivative test. There's something else called the second derivative test. Please don't get them confused. This is the test for concavity. And the reality is it looks almost exactly the same as the first derivative test. Step 1, we have to find critical numbers, but this time it's the critical numbers of the derivative. In other words, you need to find where the second derivative, not the first derivative, where the second derivative is 0 or undefined. Right? Your second step is identical to the first derivative test. You break your domain into the subintervals. Yay. Step 3 is the same as the first derivative test, kind of. For each interval, you pick a number and you plug it not into the first derivative, but into the second derivative. And all we're paying attention to is whether the thing is negative or positive. Steps 4 and 5 are where things get a little bit different, but similar, right? In step 4, for each interval, you need to write 3 statements, and I tried to model that in the last video. You'll write one thing about the second derivative. Either the second derivative was, positive. Then you'll write, oh, the first derivative is increasing, and therefore the original function is concave up. And then your 5th step, your last one, is you sort of, for each one of those, plug in that critical number and find out if it's a real point. If it is, it's a point of inflection. You can also make statements about whether something is concave up or concave down. We're now going to go on and look at the examples of these things. First example of this, where we want to analytically find the intervals where it's concave up and down and the points of inflection. So we had said that step 1 was going to be for us to find the critical points, not of the original function, but of the derivative. So we need to look at not where the derivative is equal to 0 undefined, but where the second derivative is 0 undefined. So we start by taking the derivative. First of all, we'll realize that this function is x to the negative 1. So that means the first derivative is negative x to the negative 2. And that means that the second derivative is 2x to the negative 3, which is 2 over x cubed. So just like we did before, we need to look at where this is undefined. Right? This is clearly undefined when the denominator x cubed is equal to 0. In other words, when x is 0. We also need to look at where this thing, 2 over x cubed, is equal to 0. But that's only going to happen when the numerator is 0, but 2 is never 0. So my only critical number, my only number to worry about or to work with is 0. Right? So the next step in the 5-step process is supposed to be just like very similar to the first derivative test. The next step is rewrite down our intervals. My first one goes from negative infinity to 0. My other goes from 0 to positive infinity. Right? The next step is that I'm supposed to take a number from these intervals and plug them in to the second derivative. I'm supposed to plug them into this second derivative. So I'm going to choose negative 1 here. The second derivative at negative 1 is 2 over negative 1 cubed. That's negative 2. And so my statement here is that because the second derivative is negative, that means that my first derivative is decreasing, and that must mean that the original function is concave down. It's possible that I was supposed to write that in blue. I think that might have actually been the fourth step where I write that. I get my steps a little bit mixed up. Over here, I'm going to plug in 1 to the second derivative. This is going to give me 2 over 1 cubed, which is 2. Here, since my second derivative is positive, I have that the first derivative is increasing, and that means my function is concave up. And so I just answered part of the question. Part of the question is, on what intervals is the function concave up and concave down? So using the coloring that I've been using before, this interval, it's concave down, and this interval over here, it's concave up. Okay. The last thing I'm supposed to do is I'm supposed to look at points of inflection, right? So right here in the middle, there's sort of this question about, so what happens at 0, right? At 0, there is a change between concave down and concave up. So this is a potential point of inflection. Now, why do I say potential? It's only a point of inflection if I can plug that 0 in and get a y-coordinate. So we look back at my original function. My original function was 1 over x. When I try to plug in 0, I get 1 over 0, which means this wasn't a point of inflection. In fact, because there was division by 0, we have an asymptote. There. Right? So there are no points of inflection at all, but we do have a region that's concave down and another one that's concave up. A last comment that I'll make here really quickly is that this shouldn't be surprising. You guys should know what the graph of 1 over x looks like. The graph of 1 over x has a vertical asymptote, and looks like this here and this here. Notice that this part is concave down, just like we predicted, and this part is concave up, just like we predicted. I have one more example in the next slide, and that one has some points of inflection, so it has a little bit more interesting stuff going on. So I will we'll do that example next. This is a good one for you to try on your own if you're up for it. Yeah, we just go through the 5 steps. So step 1 is where we need to find the places where the second derivative is 0 or undefined. So we know f prime of x is 3x squared minus 12x minus 18. We know that the second derivative is 6x minus 12. We consider where this is undefined. We also consider where this thing is equal to 0. It's undefined only if we have division by 0, so that doesn't happen. Over here, we find that this happens when x is 2. And so our only potential point of inflection, our only critical number for the derivative for the test for concavity is 2. Right, so our next step is where we set up our intervals. We've got one that's going from negative infinity to 2. The other goes from 2 to infinity. Our next step is that we take numbers from these intervals and plug them into the second derivative. So I'll do the second derivative at 0, because it's easy, and I'll do the second derivative at 3. Let's see here, so when I plug in 0, I get negative 12. By the way, I'm plugging these into the second derivative right here. When I plug in 3, I end up with 18 minus 12, which is 6. So in this case, I have the second derivative being positive. Oops, I'm sorry. I have the second derivative being negative. Furthermore, I think this is supposed to be the blue color. So this is where my second derivative is negative. That means the first derivative is decreasing. And that means that the original function is concave down. Right? Over here we have the second derivative being positive. We have the first derivative increasing, and therefore we have the function being concave up. So based on what we've seen here, the critical number that we were looking at here, this x equals 2 business, is indeed a possible point of inflection because it changes, the function f changes from concave down to concave up. This could be a point of inflection. All we need to do is we need to see whether or not this point works in the original function. Can we plug 2 back in? And I have that worked out over here. That would be 2 cubed minus 6 times 2 squared minus 18 times 2 plus 12. Plus 12. And if I did my arithmetic right, that would give us negative 40. At any rate, it most definitely exists. If nothing else, we know there is in fact a point of inflection, and that point of inflection is at 2 comma negative 40. So we had a point of inflection, and the other question that was asked was the intervals where it's concave down and concave up, using the coloring scheme from before. This is the one that's concave up. This is the one that's concave down. And again, our point of inflection was here at 2 comma negative 40. So hopefully that was a good and thorough introduction to the test for concavity. So get started on the homework, give those a shot, and I'll see you in class tomorrow.